when we look at cosmology, we see that we mainly have light. So there is a lot about extrapolations. And if you go back 100 years in time, we have just had so many surprises in cosmology, which just shows we just can't put the universe into a lab and do experiments with it. We have to go there, and it's so far distances. We are relying on very little evidence in the end, which still gives an interesting picture. But if we look at it, we just see that all the light that reaches us is light from the past, so we don't really know the present state. And then we have different issues that make us puzzle about our theory right now. One thing is dark energy. The universe, in order to explain the expansion rate of the universe, we need to assume that there is a force that actually stretches out space-time. So it's just not a normal process, but it's an accelerated process. If you take a balloon, for example, and you put dots on the skin of the balloon, and then you blow into the balloon, then you realize that the balloon expands slower and slower the larger it gets. And similar in the universe, we would expect, because of the gravitational force between the galaxies, that it gets slower and slower the larger it gets, because the gravitational force should actually draw it back again. But the opposite obviously seems to happen when we analyze the light spectra and interpret them in terms of distances and velocities. It gets faster and faster, the whole expansion. So there must be some force which we call anti-gravitational force or vacuum density, vacuum energy density, which is stronger than the gravitational force that would drive back the universe. So all we can say right now is that the universe is expanding very fast, and this dark energy that's responsible for that takes about 72% of the whole energy content of the universe. So that's most of the universe, actually. But that's not enough. Other observations lead us to the fact that there must be something called dark matter. That is matter that obviously does not interact with light. So the reason for that is because we see bending of light alongside galaxies, for example, and the mass of the visible galaxy would not be enough to explain the bending of the light. Then also the rotational speed of stars within galaxies varies not in a way that is consistent with the mass distribution of the visible galaxy. So scientists assume there must be something like dark matter. We have not yet an idea what that is. There are several models and we are still in search of that, but we don't know it. So that's a second dark issue within cosmology which we still face. A third problem that we have right now in cosmology is the so-called inflationary era. This is a phase in the early universe in which the universe suddenly must have expanded at a very, very fast rate, faster than today even, and then became slower again and expanded slower before becoming faster again today. And this needs to be postulated because of the distribution of energy and matter within the universe. But we have no idea why the universe as a whole should suddenly expand at such a fast rate and then slow down again and now speed up again. If you only have gravitation and the vacuum energy density, it's hard to explain that. So you need to postulate other forces that are active at that time. And yeah, so this is another puzzle, mystery with which we have to deal right now. So we see that the equations work quite well to some degree, but there are some, you could say, skeletons in the cupboard. And it might be that in 100 years people look back and just talk about us today like we talk today about Albert Einstein in the 20s of last century and say, well, at that time people believed it would be like that. And so there are limits to cosmology.